Swayam Prabha. Digital India. Educated India.
Hello. So, this course is about organometallic chemistry and my name is A.G. Samuelson. I work in the inorganic and physical chemistry department and I have been there since 1983. I teach mostly organometallic chemistry and inorganic chemistry, and this course is a result of my experience with the students in introducing them to organometallic chemistry. So, organometallic chemistry is in fact a very complex field and it is a fascinating field. What this course does is to have a structured introduction to it, so that even if a person has not studied any organometallic chemistry in the earlier days, he can boldly start reading the literature in organometallic chemistry after going through these few lectures. So, let us take a look at the slides one by one. We have a structured introduction, as I said, but it is definitely a very fascinating field. It was a late comer into the subject field of chemistry. It was only in 1956 that people realized that organometallic chemistry is a discipline, a sub-discipline of its own, and it has a significant amount of material that would be of great interest, not just in the laboratories, but also in the industry. The problem with organometallic chemistry is the fact that suddenly the student is presented with a large number of new concepts which are not available or necessary to understand organic chemistry, or for that matter even inorganic coordination chemistry, classical coordination chemistry. So, now we first answer the question, why study this particular field if it is so complex, and if it is interesting, then it must be worth it. So, let us take a look at some reasons why we should study it. I have developed here a few questions that one should ask when you look at any new discipline. And the first question that I ask is that, are there any significant discoveries in this field that has merited, for example, the award of a Nobel Prize? Now, at least in the sciences, it is well known that the Nobel Prize is considered as one of the best prizes or one of the top prizes that are given to a scientist who has made a very important discovery which would benefit mankind. And so, we can ask this question, has organometallic chemistry really achieved that status, so that some people working in this field would receive the Nobel Prize? Let us see what happens to that question. Then we ask the question, we look at some of the journals which are of importance to all scientists working in the area of chemistry. Do we see any organometallic chemistry papers, and what kind of papers are they? And let us see what kind of research is funded, and then finally, how much of the economy is really driven by this topic. So, each one of these questions will be briefly answered before we proceed to the subject itself. So, let us take a look at the Nobel Prizes. Here I have listed for you some of the Nobel Prizes that have been awarded in the general area of organometallic chemistry. As I said, the subdiscipline was recognized only in the late 1950s, and surprisingly by 1963, Ziegler and Nutter were awarded the Nobel Prize for working in the area of titanium and zirconium catalysts which were capable of producing high molecular weight polymers, especially polyethylene and polypropylene. And polypropylene was made in a stereospecific fashion, which resulted in very interesting and very valuable properties for polypropylene. So, this area continues in spite of the fact that the major discovery was made in 1963. Even today, it continues to be an active area of research. And through the series of lectures, we will see how this is quite important and what a fundamental reaction in organometallic chemistry is responsible for this particular discovery. Next, let us take the Nobel Prize that was awarded to Wilkinson and Fisher in 1973. That came just 10 years after the first Nobel Prize to Ziegler and Nutter, and Wilkinson and Fisher were actually awarded the Nobel Prize for their discovery of metallocenes, and this discovery was in fact the key discovery that spurred people on to studying organometallic chemistry as a subdiscipline. By then, it was very clear that it was this seminal discovery and the subsequent research work that was done in this area that was going to contribute significantly in chemistry. I next talk about the discoveries made by Herbert Brown and Wittig and Lipscomb. I take these two Nobel Prizes together because it turns out that all of them contributed to the chemistry of elements on either side of carbon. Brown contributed to the chemistry of boron, Wittig to the chemistry of phosphorus, which is on the next side and the right side of the periodic table, where carbon is there in the center. So, Lipscomb and Brown contributed significantly to the understanding of the chemistry of boron and the structures. These are key discoveries in organometallic chemistry because they helped one to understand some of the structures which were not available in the literature in earlier days. So, next comes the discovery or the Nobel Prize to Fukui and Hoffman. Once again, Fukui and Hoffman were given the Nobel Prize for their contribution to the structures of compounds, and they used frontier molecular orbital theory, but Hoffman applied it completely to organometallic compounds. He was able to explain the structures of all the new compounds that were discovered in the 60s and 70s by researchers working in organometallic chemistry, and also suggest a framework for understanding the structures that would be discovered in the future. So, that was a seminal contribution to the field of organometallic chemistry. There was a long gap since from 1981 to 2001, and in 2001, Sharpless, Knowles and Noyeri were awarded the Nobel Prize for their contributions to asymmetric catalysis, and this was completely in the field of organometallic chemistry, where chiral ligands were used by these workers to generate chiral compounds, which were very important in the field of drug discovery. So, Noyeri, Knowles and Sharpless were recognized for this key contribution in 2001. This was rapidly followed by another two Nobel Prizes in 2005 and 2010, and in 2005, Schrock, Grubbs and Chauvin were awarded the Nobel Prize for their work on metathesis chemistry. Interestingly, this deals completely with carbon-carbon double bonds and double bond containing compounds and how they can be transformed from one to the other. It turns out that the new bonds that are formed were also double bonds, and so this turns out to be a contribution that is not paralleled in classical organic chemistry. This was followed by Heck, Negishi and Suzuki, who contributed significantly to the formation of a carbon-carbon single bond. So, these two discoveries in 2005 and 2010, these two Nobel Prizes recognize the contribution of organometallic chemistry to the formation of carbon-carbon single bonds and carbon-carbon double bonds. If you look at the span of say 50 odd years from or 60 years from 1955 to the 2010, you see that there are about 8 Nobel Prizes that have been awarded to the field of organometallic chemistry. And even earlier the discoverer of salvarsan, which is inorganic or organometallic drug that was given to treat syphilis, was also someone who received the Nobel Prize for in the field of drug discovery, but then it was an organometallic compound. So, you can see that several Nobel Prizes have been given in this field, and so now let's take a look at briefly at the journals and how they give importance to the subject of organometallic chemistry. Now, if you look at any one of these common journals which are on the top of the list of any researcher, like Journal of American Chemical Society or Chemical Communications or Anglo-Antichemy, these journals are journals which are publishing in the general area of chemistry, and if you open any issue, you will find that there are at least 2 or 3 articles on organometallic chemistry. So, I have put for you to in this projection here just one instance of article written by Shilov and Shulpin about CH activation. This turns out to be a very important reaction which has been made possible because of organometallic compounds and organometallic chemistry. So, you can see that once again organometallic chemistry is extremely important in inorganic chemistry and in chemistry in general. Once again, early transition metals were shown to be good metals for transition metal CH activation, but recently it has been shown that even late transition metals with appropriate set of ligands can carry out ligand directed CH activation reactions, and this work has been carried out by Melanie Sanford and her co-workers. If you look at the field of organometallic chemistry, it's not as if everything that needs to be discovered has been discovered. So, here I have a article which is appeared on the journal Nature, and you find that they have discovered something extraordinarily new even in this last 60 years. What was not known has now been newly discovered. So, here is an example of a reaction between a molybdenum complex, where molybdenum is in the 0 oxidation state and it has got 6 phosphorus ligands around it. So, here is the ligand that here is the compound that we are talking about. When it's reacted with this organic compound, it forms a very interesting and novel complex, where the metal initially coordinates to the ring, where there are 2 nitrogens. So, it is a phenazine ring that is having the nitrogen on the aromatic part of the ring. And then after some time, if you heat it further, then the molybdenum moves over to the ring which has got only the carbons. So, here are some challenges about why this happens and what are the reasons which initially stabilize the nitrogen containing ring coordinated to the molybdenum, and later what is the thermodynamic preference for the carbon containing ring. Interestingly, if you just move from molybdenum to tungsten, one would expect very similar reactivity, but surprisingly the same reaction which was carried out with tungsten now suggests that the reactivity can be extremely different, and you have extraordinarily novel compounds where an aromatic ring system has been broken and a carbon-carbon ring has been broken, carbon-carbon bond has been broken, and that too part of an aromatic ring, and that forms a metalla cycle. So, here is the set of atoms that we are talking about, and that forms a ring, and that ring turns out that that ring is an aromatic ring to start with. Here is the ring, and that has been broken by the tungsten. So, you can see that some extraordinarily novel complexes can be generated, some things that challenge our understanding of chemistry in general and help us to think about what could be coming in the future. Here is another challenge that has come up very recently in 2005. Graham Ball and co-workers have shown that even xenon, which is a zero group element or an inert gas, what was originally considered as something that would not react with any other element, what was called inert gases or the zero group, that turns out to be an element which can form an organometallic compound. Let's see what they have actually done. Here is the reaction that they have carried out. A rhenium complex, which was excited with a xenon flash lamp, absorbs light and in the excited state loses one of the ligands. If it loses the xenon, if it loses the carbon monoxide, then the xenon appears to coordinate to the rhenium. And in this particular state, it is possible to see the xenon phosphorus and xenon fluorine coupling constant. So, this was carried out by labeling the xenon. So, they carried out the reaction in the presence of 128 xenon, which is NMR active, and they were able to show that in fact, there is a covalent interaction between the xenon and the rhenium. That's the only way in which you can have this type of a weak coupling constant between the xenon and the fluorine. So, you can see that there are surprises galore and there are challenges that have to be addressed in the field of organometallic chemistry. And if you ask these two last questions to see what research is funded, how much of it is driving the industry, once again organometallic chemistry comes out on the top. You can take all the journals that publish organometallics and you can see that the number of papers published are significantly large. Close to 2,400 papers have this concept of organometallic chemistry mentioned in their papers. Or if you look at the key papers, if you look at the topics that are mentioned, you see that organometallics are there in at least 1,400 papers every year. So, it turns out that this is a very active field of research, and even if you look at the industry, it looks as if you have a large number of industries which employ organometallic compounds either as catalysts or as additives and as part of the process which is there in the industry. So, here I have listed some of the silicons and organolithium compounds. Organolithium compounds are used significantly in fine chemical synthesis. Silicons are used in various industrial applications and they are elastomers and so on. So, metal complexes are very commonly used for making polymers, especially polypropylene and polyethylene, which are made in tonnage quantities. These molecules are made using organometallic catalysts, which are basically the result of Ziegler-Natta's work. And then there are other small molecules like acetic acid, acetaldehyde and several other small molecules which are generated from carbon monoxide, hydrogen and readily available starting materials, and this is again made possible by organometallic compounds. And we will see some of these reactions and how these are how these unique reactions are made possible because of organometallic chemistry. So, we have looked at a variety of questions. Are there Nobel Prizes? Are there important papers published in journals? Is this research well funded? And what is practiced in the industry? In all these cases, we have come up with positive answers for the field of organometallic chemistry. So, now we ask the question, why is this subject so important? Are we dealing with a special element? Organic chemistry, for example, deals with this very special element of carbon. What about organometallic chemistry? Is it the same fact? Is it because of carbon? So, if I ask the question, what is special about carbon, you would probably come up with these answers which I have listed here. Carbon is unique because it forms bonds to other carbon and it forms strong multiple bonds, and it forms strong multiple bonds to in a cyclic fashion, so that the molecules are called aromatic. So, if I list all these things, I would still say this is not the reason why organometallic chemistry is so special. Carbon has in fact an electronic configuration of 1s2, 2s2 and 2p2, and this is in fact special. Why? The answer is that when it forms 4 covalent bonds in order to generate the noble gas configuration, the molecule can do so by hybridizing 2s and 2p. The gap between 2s and 2p orbitals are just right. So, the promotion of the electrons from the 2s and 2p orbitals are easy and 4 equivalent covalent bonds are formed. That leaves carbon with no extra electrons and no vacant orbitals. This is extremely important and is probably a fundamental fact which makes carbon a unique element. Now, when it comes to transition metals, you will notice that transition metals are exactly the opposite. They always have vacant orbitals, almost always, or they have extra electrons. Rarely do they keep a noble gas configuration. In the case of transition metals, the noble gas configuration would usually be an 18 electron configuration. So, here I have shown for you some of the stable coordination compounds that are available in the literature. Most of them are octahedral complexes formed by the 3D transition elements, 3D 2 plus ions or 4D 2 plus ions and 3 plus ions, and you will notice that many of them or most of them are not 18 electron species. To look at the valence electron count, you just count the number of valence electrons on the cobalt. If it is cobalt 2 plus, then you would have 7 electrons, and with 6 water molecules, each one of them would donate 2 electrons each. And so, if you add up, you would end up with a valence electron count of 19. So, that is one more than 18. And similarly, for nickel, it would be 20. For the vanadium echo complex, it would be 15. So, very few complexes would really have 18 electrons. So, it neither has a full shell, and it always, many times, it has less than 18 or more than 18. So, what happens in transition metals to the transition metal in transition metal organometallics? If you look at most of the compounds, they follow the 18 electron rule. So much so that it is important for us to look at this rule briefly to see how this rule can be verified when we write a structure to see if it would be a stable compound. Most complexes with transition metal carbon bonds force this preference. So, they always have an 18 electron count. So, when carbon combines with the transition metal, both the metal and the carbon lose their identity. In what way has carbon lost its identity? So, here is an organometallic compound that I want to show you for just illustration of the fact that carbon in this molecule is in a very strange environment. Very rarely would carbon, or rather almost always, it would have a 4 coordinate geometry, and that also it would be a tetrahedral geometry if it has only single bonds. But here is a molecule where carbon is having 5 atoms around itself. Now, look at the coordination geometry around the iron. That is no longer octahedral either. So, that has got a geometry which is non-octahedral, and the carbon has got a geometry which is non-tetrahedral. So, both carbon and the transition metal lose their identity. So, here is another example. We all know that cyclobutadiene is a rectangular molecule, because if it is square, it would be anti-aromatic. So, it turns out to be equilibrating between 2 rectangular structures, and when it forms a iron carbonyl complex, lo and behold, it changes its character. It keeps a strictly square structure of 4 carbon atoms. So, you can see that now carbon has lost its character of being anti-aromatic when it has got 4n pi electrons. So, here is another example which is from an aromatic molecule like chlorobenzene. If you treat it with ammonia and heat it any amount, it will not carry out such a nucleophilic substitution. So, nucleophilic substitution for an aromatic compound is not possible in classical organic chemistry. But if you do this with a transition metal attached to the aromatic ring, it is now possible to carry out this simple nucleophilic substitution. So, nucleophilic substitutions which were not possible in classical organic chemistry now becomes easy when you have a transition metal coordinated to the ring system. So, are we dealing with a special element? The answer is probably no. We are dealing with a special combination of elements, the combination of transition metals and carbon. So, there are very interesting challenges which this combination throws at us. First of all, we can synthesize some new and interesting molecules which have extraordinarily new interesting reactivity patterns, what was not possible with classical organic chemistry. Activation of inert molecules, for example, methane or even carbon dioxide or the carbon fluorine bond, turn out to be challenges which are still being handled by organometallic chemists. So, there are other things also like catalysis. Catalysis by organometallic chemistry is quite popular. It is indeed feasible, but can we approach the efficiencies of enzymes? Can we use organometallic compounds to catalyze reactions at extremely fast rates? And finally, asymmetric induction in catalysis is also a major challenge. And as I had mentioned just briefly, it was for this contribution that that 3 people received the Nobel Prize in 2005. So, I want to introduce to you now the organization of this course. As much as possible, we have kept it modular based on the ligand systems. Now, so one would ask the question, how are the ligands classified? In organometallic chemistry, the ligands are classified according to the hapticity. Hapticity is indicated by the symbol eta, and eta indicates the number of carbon bonds, number of carbon metal bonds that can be seen when you have a transition metal organometallic compound. So, if I have a 3 carbon framework and if all 3 carbons are within bonding distance, if all 3 carbons are within bonding distance to the metal, then I would call this an eta 3 compound. Whereas, if the same compound is present in such a way that the metal is interacting with only 1 carbon, if it is interacting with only 1 carbon, then I would call it a eta 1 compound. So, the hapticity of the ligand is really a key to understanding and unraveling organometallic compounds. And many times the hapticity can change, and this is called fluxional behavior, and this is something which we will deal with during the course of this particular set of lectures. Let me just now show you how we have organized the lectures. So, in many textbooks, synthesis, structure and bonding of organometallic compounds with common ligands are shown initially, and then we have reactions and we have properties. Now, in this course, during the course of these lectures, we will not strictly follow this order, but let me introduce to you the way in which the ligands with metal carbon bonds are classified. Let us take a look at that first, and then we will see how we have presented the topics in this particular course. So, ligands with metal carbon bonds, if we only look at the metal carbon bonds, you have a very large number, but based on hapticity, you can see that many of them, or a large significant number of them, have got a single carbon attached to the metal. So, these are all eta 1 carbon ligands. So, they can be alkyl, aryl, or for that matter vinyl, and you can also have small ligands like carbon monoxide and carbenes. Carbon monoxide and carbenes are all single carbon bonded systems. And then you have the odd number of carbons attached to the metal on the top. These are odd. And then I have listed for you even number of carbons attached to the metal on the lower half. So, you will notice that the odd carbon attached metal complexes are usually indicated as anionic ligands, and we will talk about the nature of this interaction in a few minutes. So, on the other hand, even carbon atoms that are linked to the metal are usually neutral ligands, and many of them are known with transition metal interacting with them. Many of them are known where transition metals are interacting with even number of carbons. Then there are non-carbon ligands which support organometallic chemistry. This is a situation where there is one metal carbon bond, but the rest of the metal complex has got either a ligand with a phosphorus or a hydride or a nitrosyl. These do not have a metal carbon bond by themselves, but nevertheless they support organometallic chemistry or modify the properties of the organometallic chemistry. So much so that we need to know a little bit about the chemistry of these molecules if we have to understand organometallic chemistry. So, we are going to deal with these ligands as well. Now, if you look at the reactions, once again we can go from the simple ligands, the reactions of the simple ligands to the more complex, but it is more convenient to classify them by the type of reactions that they undergo. The simplest, of course, is substitution and isomerization, and these are listed for you on the top, followed by what is unique to transition metal organometallic chemistry, which is called an insertion reaction. So, normally insertion of an anionic ligand occurs when the anionic ligand migrates to the neutral ligand. So, we will look at these reactions, and we will do that right after we talk about metal carbon containing compounds where there is only a single carbon attached to the metal. Subsequently, we can also see that there can be an oxidation state change in the transition metal when you have an organometallic compound. So, you have oxidative coupling of neutral ligands like a carbene and an olefin. That is the basis for the famous metathesis reaction. Then you can also have oxidative additions of molecules like methyl iodide and elimination of such molecules, including the elimination of 2 atoms of hydrogen, for example, on a metal, that would result in reductive elimination. Here there is a oxidation state change on the transition metal. So, initially we will consider those reactions where there is no change in the oxidation state, and then we will look at those where there is a change. If you look at the properties, there are several properties which are very interesting for organometallic compounds. We will not be always dealing with these with these examples, but towards the end of the course we will deal with some cases where organometallic chemistry has turned out to be an extremely important and valuable addition to the arsenal of the chemist. So, in the current approach, we will try to deal with these ligands in a systematic fashion, going from the simple to the complex ligands. Until we discuss the complex ligands, we will not introduce them as much as possible in the early part of the course. We will try to integrate the discussion of reactions with the new structure types. I have found that this keeps the interest of the person studying the subject so that first we do not deal with completely structures and then move completely over to reactions. So, there has been an integration done of the reactions and the structures, and you will see the value of doing that in a structured fashion. So, when it comes to textbooks that are available in the literature, there are several new textbooks that have appeared, but I would strongly recommend that if you are a serious organometallic chemistry student or even a serious chemistry student, that you have at least one book on organometallic chemistry. And in recent times, there's a book on organometallic chemistry that has been written by B.D. Gupta and Anil Elias, which has been published by Universities Press, which is quite affordable and readily available for the chemist. So, let's take a look at electron counting the organometallic chemist's way. And unfortunately, as I had hinted earlier, there are two ways in which the organometallic chemists or some organometallic chemists count the number of d electrons which are accessible to the metal. So, let's take a look at some of these methods. First, we should mention that these counting rules are only to keep track of the number of electrons. They are not to be confused with the charge that is present on the metal or, for example, on the ligand. Nevertheless, we will talk about ligands as if they are ionic or as if they are neutral. And this bookkeeping is important only for us to find out if the molecule will be stable or will it undergo some reactions or will it undergo some redox reactions with other oxidants or reductants. So, when you want to look at a metal complex which has got a net charge, these electrons are usually, if you have excess electrons, then they are added to the metal atom, so that you have the net charge of the species which is inside the square bracket matches the charge which is present outside the square bracket. Let's take a few examples and then this would become fairly clear. If you take a simple complex like Cp2TiCl2, Cp stands for the cyclopentadienyl ligand. So, the cyclopentadienyl ligand is a system which has got 5 carbons, and because it is C5H5 minus, it is obvious to see that this has got 6 pi electrons, and if it has 6 pi electrons, it is an aromatic ligand system. Now, it turns out that this aromatic ligand system will readily coordinate to a variety of metals, and if it two of them coordinate to titanium, you can have this complex Cp2TiCl2. Now, let us take a look at at a set of ligands where we have for us the two methods listed out. So, let us go from the simple ligands. If you have a ligand like hydrogen, then in the ionic method, you would assign it a charge of -1. If it has a charge of -1, hydrogen already has 1 electron around it, and so a -1 charge will necessarily mean that it has got 2 electrons. So, this turns out to be a 2 electron donor. Whereas, in the neutral method, this is the neutral method, you would only count the number of electrons which are there on the ligand to start with. You would not attribute a charge to the ligand if when it is not there. Here, for example, for hydrogen, we would indicate that it is a 1 electron ligand. Now, you might wonder, why do we confuse this issue by having H minus? Very often, hydrogen is more electronegative than the metal. So, when it is coordinated to the metal, the assumption is that hydrogen acquires 1 electron from the metal, and so the metal becomes +1 and hydrogen becomes -1. So, 1 electron is transferred from the metal to the hydrogen. So, this turns out to be correct. For example, in the next case, when you have a halogen, it is very obvious that halogen is extremely electronegative. And if so, when it coordinates to an electropositive element like a metal, then it will acquire a negative charge and it will become X minus. So, all halogens are indicated as 2 electron donors, but in the neutral method, you still count it as a 1 electron ligand. So, you can see that none of these methods, either the ionic method or the neutral method, is a perfect method. Both methods have their advantages and disadvantages. But what is interesting and what is important is that you use the methods consistently. You cannot use the ionic method for some ligands in a metal complex and the neutral method for some other ligands in the same complex. That would lead to a wrong result. So, let us take a look at some of the other ligands which are listed here. Cyanide, for example, is an electronegative group and it is indicated as Cn minus, and it is usually bonded through the carbon. It is in the neutral method, it is considered still as a 1 electron ligand. Each of the methyl radicals or any alkyl radical is indicated as an anionic species. This again turns out to be confusing at times because carbon can be just as electronegative as a metal atom, or sometimes it can even be less electronegative, but still we consider by convention carbon to be more electronegative and indicated as an anionic ligand. So, all these species turn out to be simple species where you have a 1 electron donor in the neutral method and 2 electrons in the ionic method. Next comes carbon monoxide. Let us leave nitric oxide for the moment and deal with carbon monoxide. Carbon monoxide has got a lone pair on the carbon end of carbon monoxide, and that means it donates 2 electrons. Here we have no confusion between the ionic method and the neutral method. Both of them suggest that 2 electrons are donated from the ligand to the metal. Similar is the case for ammonia or water. They are 2 electron donors, whether they are neutral or ionic, it does not matter which method you use. A carbene, which is what is indicated here, carbene is also a 2 electron donor. So, you can imagine a carbene as a carbon containing a lone pair of electrons. So, that can donate 2 electrons in either method. And subsequently, we should look at isocyanides. Here are isocyanides, and isocyanides again have got a lone pair of electrons situated on the carbon. So, they are not confusing. They will be 2 electron donors whether you consider them in method A, which is the ionic method, or the method B, which is the neutral method. So, ethylene is a molecule which is an unsaturated organic molecule which has got a pair of electrons in the pi orbital, and this can donate a pair of electrons, and so we have a neutral species which is giving 2 electrons. Now, let us come back to nitric oxide. Nitric oxide, because nitrogen is more electronegative, we can transfer an electron from the metal to the NO, and then it will become NO minus. And this 1 electron that was sitting in the antibonding orbital will now have another electron in the same orbital, and these 2 electrons can be donated to the metal. So, NO, if it is, especially if it is in a bent form, so if the metal is having a bent NO, then we end up calling it as a nitrosyl, bent nitrosyl, which can donate 2 electrons, and it is counted as a negative ligand in the ionic method. In the neutral method, of course, we will consider that only as a 1 electron donor. oxido and sulfido ligands are rarely encountered in organometallic chemistry, but they are all 2 electron donors when it comes to the neutral method, and when it comes to the ionic method, now it will have to be considered as 4 electron donors. So, I guess this set of this classification helps you to follow the general trend which is there in the literature. They might either use the ionic method or the neutral method in order to assign the electron count. Now, in this next panel, I have now for you a linear nitric oxide. A linear nitric oxide is a system where one electron from the nitric oxide antibonding orbital is transferred from the ligand completely to the metal. And so, sometimes in the ionic, not sometimes, but always in the ionic method, you will consider that as NO plus. So, this is a first example that we are considering where the ligand is positively charged. So, although NO is more electronegative as a group than a metal atom, if it is a linear nitric oxide, then turns out that you can transfer the electron completely to the metal, and you consider that as a 2 electron donor which is positively charged. Similarly, an allyl group can be considered as a 2 electron donor if it is positively charged, and that is quite obvious because you would have a double bond and then a positive charge at the allylic position, and so it would have only 2 electrons which it can donate to the metal. So, carbines are unusual. We will leave them for the moment and look at other examples. These are classical ligands: ethylene diamine, bipyridine, butadiene is just an extension of ethylene. So, all of them will give 4 electrons each, whether they are in the ionic method or the neutral method. Similarly, benzene will give 6 pi electrons, and that is again for the sake of electron count. It is not as if the electron is completely transferred to the metal. Whereas, in the case of C5H5 minus, it is obvious that the metal will be positively charged and the ring system will be negatively charged. So, you have a 6 electron donor in the case of the cyclopentadienyl anion. In the neutral method, we do a bit of violence to this concept and we say that it gives only 5 electrons. Now, there are some advantages in using the neutral method because it is easy to forget the fact that the metal is changing its role or the ligand is changing its role. We just count the number of atoms which are coordinated to the metal and keep that as the number of electrons that are donated to the metal. So, C7H7 for example, we would not have to consider whether it is aromatic or not. If all 7 carbon atoms are bonded to the metal, then we consider that as a 7 electron donor. So, now let us come back to the nitrido case. This is an example where in a simple minded fashion, if you use the neutral method, we would think that there are 3 electrons which are donated to the metal. So, in other words, there are totally 5 electrons which are there for the nitrogen. This is the valence shell, but if you consider this as a nitrido ligand, then you would write it with a triple bond to the metal. So, here is the metal and it is forming a triple bond with these 3 electrons, and you have only a lone pair on the nitrogen which is present on the nitrogen side. And so, you have a metal which is coordinated with a triple bond to the nitrogen. So, then in the neutral method, you take it as a 3 electron donor. In the ionic method, you look at it as if it is a N3 3 minus. So, you would end up with a total of 6 electrons on the nitrogen. This is an unusual bonding situation, but that is the way we count it. Surprisingly, for a carbine, a similar situation should occur, but in terms of electron count, people have always used a 3 electron count for the ionic and the neutral method. And so, that is why I have marked it with a red color, because that is an exception which is not following the convention that we have followed right through in this whole in this list of ligands. So, when you count electrons, you either should follow the method A, which would have charges on the ligands when it is appropriate, or you should stick to method B, where you would ignore the oxidation state of the metal. You count the total number of d electrons for the metal as if it is in the 0 oxidation state. So, you just assume that it is in the 0 oxidation state, and you add the number of electrons that are coming from the ligand, irrespective of what you might think is the charge on the ligand. So, let us take a few examples, and then this will become easy to follow. And what is interesting or what is important is that with either method, we should end up with the same result, and that is the most important fact. And it is important that you practice with some of the compounds, so that you will understand what is going on. So, let us take a look at the first compound, HMnCO5, that you are going to talk about. HMnCO5, hydrogen, because as I mentioned to you, in many cases it should be considered as a more electronegative element than the metal, and because we can't figure it out, the ionic method always takes it as H minus, and if it is H minus, it is a 2 electron ligand. So, it is a 2 electron donor. Then, if this is H minus, and if the complex is having no charge, that means something else in the metal complex should have a charge. So, if H is H minus, then we have to put a plus charge on the manganese, because we know that carbon monoxide is a neutral ligand. So, 5 carbon monoxides give you 5 into 2, 10 electrons total, and H minus is given 2 electrons, and we have removed 1 electron from the manganese. We have removed 1 electron from the manganese, and manganese had 7 electrons to begin with. So, we end up adding 6 electrons as a contribution of manganese, and the total turns out to be 18 electrons. So, we achieve this 18 electron rule by counting it in this particular fashion. Now, let us take a look at the neutral method. So, this is a typographical error. So, this should be the neutral method. The neutral method, we have manganese as if it is in the 0 oxidation state. It has an electronic configuration of 3d5, 4s2, which adds up to a total of 7 electrons. So, then you have hydrogen, which we will now consider artificially as if it is H dot, and so that will contribute only 1 electron. And 5 carbon monoxides will give 10 electrons, and the total will again be 18 electrons. So, you can see that whether you use the neutral method or the ionic method, you end up with a total of 18 valence electrons. Now, let us take another example where there is a charge on the metal because of the net charge on the complex. So, this is a complex which has got a net negative charge. There is a charge on the complex which is indicated as a charge after the square bracket. So, this charge adds to the total number of electrons that are present in the valence shell. So, carbon monoxide, 3 carbon monoxides are there. So, we end up adding 6 electrons for the same. PF3 is like PR3, it would donate 2 electrons. 2 valence electrons on the phosphorus will be donated to the metal. Now, we have a net negative charge on the complex, and neither of these 2 ligand systems are charged. And so, what we have to do is to add this extra electron on to the rhodium, which is the metal. So, this negative charge is added on to the metal, and that is why we consider rhodium as rhodium minus 1. Rhodium had 9 electrons to start with, valence electrons, and with 1 extra electron, it becomes a 10 electron species. So, the total adds out to be 18 valence electrons. Now, in a similar fashion, in the neutral method, what we do is to take the rhodium, which had 9 electrons in the valence shell, PF3 2 electrons, and 3 carbon monoxides 6 electrons. And because we had an extra charge on the whole complex, that extra charge is added separately, and as a result we would again end up with 18 electrons. Now, let us just think about this for a moment. If there was a net charge plus 1 indicated by a plus charge in a metal complex MLN, then we would have to subtract 1 electron from the valence shell in the neutral method. In the neutral method, we would have to subtract 1 electron. If there is a negative charge MLN and then we have a negative charge, then we end up adding this 1 electron. So, it's important for us to note that both of them come at the same result as a result of this addition. So, once again, ferrocene, the analog of ferrocene is ruthinosine, and that is what we have here. We have C5H5, which would donate 5 electrons in the neutral method. So, 5 into 2, 10, and we have 8 electrons from ruthenium, and it ends up with 18 valence electrons for the ruthinosine. Similarly, C5H5 minus would be an anionic ligand. So, 6 electrons from each C5H5 minus, that gives us 12 plus 6, and that is 18 valence electrons. So, either method gives us the same number of valence electrons, but only thing that we have to remember is that we have to be consistent as we go through this electron counting. So, during the course of this series of lectures, we will always be consistent and either use the neutral method or the anionic method. Nitrosyls are one example where the situation is very complicated, and one needs to know whether the nitrosyl is in a linear fashion or whether it is in a bent fashion. When it is in a linear fashion, it is close to 180 degrees, the angle is 180 degrees. Then in the ionic method, it is considered as a positive ligand. NO is considered as NO plus, and that is very important. And then it is considered as a 2 electron donor, whereas in the case of the neutral method, it is considered as NO, and then it is considered as a 3 electron donor, but the net result would be the same. So, with this we end today's lecture, where we have considered the classification of various ligands and how we look at them by their hapticity. The hapticity is a number of carbon atoms which are attached to the transition metal. And we have also seen that the number of electrons that are donated can either be based on the ionic method, which makes carbon, hydrogen and nitrogen and halogens more electronegative, and so they are assigned negative charges, artificially given negative charges. And in the case of the neutral method, we consider them as if they contribute 1 electron each. So, we will continue with this series of lectures where we will talk about one ligand after the other, starting with carbon 1 containing systems.